First of all, I want to say thank you for the dubious distinction of being selected by the DREGS nominating committee. I was flattered to be invited. I have, at times in the intervening 6 months or so since this talk was supposed to have been delivered, I have questioned the wisdom of my saying yes to that invitation, but nonetheless, here we are, and I'm looking forward to it. Corey, are you seeing my screen appropriately going out to everybody? Apparently, yes.
Yeah, I see it just fine, John.
Okay, good. So my topic tonight is, is the result of distillation of many years of interest in gold deposits and precious metals in high-chloride brines. And to sort of set the stage and introduce the topic, I have to go back into sort of ancient history, back into the 90s, to a project that I was working on in Canada. So what I have been concerned with, excuse me, what I've been concerned with is the possibility that gold and platinum group metals can be carried in low temperature, high chloride basin brines with geological and chemical controls similar to those for the copper and silver in sandstone hosted copper deposits, the uranium and unconformity uranium deposits, or zinc, lead, and silver in SEDEX deposits. All of these deposits are unified by having been deposited by brines with considerable salinity at relatively low temperatures, generally between 100 and 250 degrees centigrade. The conclusion that I've come to after many years is that the available data supports a pragmatic argument for sandstone or shale-hosted gold or PGE deposits with or without significant base metals that are underexplored and probably ought to receive considerable more attention. And to set the sort of the ground rules, the deposits that I'm speculating about are sediment-hosted gold deposits where the gold was transported in a brine as a gold chloride complex. What I'm not speaking about and don't want to be confused with are Carlin type gold deposits, which are generally deposited from low salinity fluids with gold carried as a bisulfide gold complex. So with those sort of ground rules, I will diverge into the background information and talk a bit about prairie gold, which was something that myself and several colleagues pursued in the mid-90s. It died an untimely death with the DREGS scandal in '98, and the company and the claims in Canada went away. But prairie gold was a concept and a series of prospects in the Canadian Interior Platform, which is this green part of Canada just east of the Canadian Rockies, between the Canadian Rockies and the Canadian Shield. The section there is Paleozoic carbonates and evaporites overlaying basement rocks. And then on top of the Paleozoic section are Cretaceous clastics with the tar sand deposits in. So we'll take a little bit closer look at the Alberta just to set this stage. So this structure through here, north, the east trending structure is the Peace River Arch, which is an anticlinal structure that was active in the Devonian. It plunges underneath the Canadian Rockies, and at the upper end of the Peace River Arch in the Fort McMurray area, there are gold and PGE placers in the Athabasca River. And those attracted the attention of a number of companies and the Canadian Geological Survey in the 90s. And we were all trying to find out, or how the gold and PGE came to be so far removed from anything that looked like a reasonable source for gold and platinum in the sands of the Athabasca River. To set the stage, along the Peace River Arch here, there is in the Devonian section, there is a several 100-foot thick evaporite, mostly salt, called the Prairie Evaporite. At the upper end of the arch, there are salt springs that are emitting considerable amounts of salty water immediately under and adjacent to the tar sands deposits. And in the Devonian limestones, normally on fracture surfaces, there is native gold deposited as small microprobes size identifiable grains on those limestone fracture surfaces. So how did the gold get there? Well, we seized upon a model that Garvin had used to explain the Pine Point deposits, which are further to the north and east, but also at the edge of this interior platform section. And in here we have the Paleozoic section in Garvin's model with fluid flow driven from basically from the high head of the Rockies down and out through the carbonate to the Pine Point deposits out here to the northeast. Myself and Hugh Abercrombie adapted this model to what we called prairie gold, where we saw this hydrologic system of water from the Rockies actually mobilizing high chlorine brines from the evaporite section up the Peace River Arch, leaching and altering gold and PGEs out of the basement rocks and depositing that gold in the section immediately under the tar sands, which is this little green puddle here at the northeast end of the Peace River Arch. So that was the beginning of pursuing gold and PGEs in high chlorine brines. As I said, it died and assassinated by Felderhoff and the other folks from the DREGS scandal. But the idea hasn't gone away. And so I refer to basin gold as sort of the son of prairie gold and sediment-hosted copper-silver deposits. Now, to explore this, I'm going to take another diversion into the sediment-hosted copper-silver deposits, particularly the Kupferschiefer in Germany and Poland, which is the granddaddy of them all. Copper deposits in the Permian sediments of Germany and Poland, in the Kupferschiefer, Zechstein Basin. And there are significant deposits in Mansfeld-Sangerhausen. It produced something like 108 million tons of 2.5% copper plus 120 grams of silver. In Poland, the Lubin-Sarowitz district is still producing and has production and reserves of 3.4 billion tons of 2% copper and a little over an ounce of silver. One of the things that attracted my attention to this deposit, other than the fact that I've been pursuing sediment-hosted copper-silver deposits for many years, was an article published by Pietrzinski and Wódzicki in 2000, where they announced the discovery of a gold deposit underneath and immediately adjacent to the Lubin-Sarowitz district that contained 1.5 grams gold, 0.3 grams of palladium, and 0.2 grams of platinum. Now, the Kupferschiefer copper deposits have been mined for a long time. The cartoon or the woodcut on the left there is from Gregorius Agricola from 1550. He was largely writing about the copper mining industry in Germany and Poland in the Middle Ages. Now, the Zechstein Basin of Northern Europe stretches all the way from the eastern coast of England, Anglia, clear across Poland into the western states of what used to be the Soviet Union. The copper deposits occur along the southern margin of the basin. The Mansfeld-Sangerhausen is here in Germany. The Lubin-Sarowitz Basin is here in Poland. This is a stratigraphic section of the Kupferschiefer deposits and section. The basal part of the section is a red sandstone unit called the Rotliegende. It has in its base some altered volcanics, but it is a several thousand meters of red sandstone. At the top of the sandstone unit, there are two, what I suspect to be altered units, a Grauliegende, a gray sandstone, and a Weißliegende, the white sandstone. And the white sandstone appears to be red sandstone that has been bleached by epigenetic alteration. Immediately overlying the sandstone is a few meters of a very organic, rich black shale called the Kupferschiefer, copper shale. That's overlain by the Zechstein dolomite or limestones and dolomites, and then by the Werra anhydrite, which is largely salt. So here we have an evaporite basin that transgressed across this Permian red bed sequence. We have a very pronounced redox boundary here at the top of the sandstone unit. We'll see this section again and later, but I want to note that the gold deposit in Poland occurs right here in the sandstone and in the very lowest parts of this black shale horizon. Now, the black shales have been known to host metals for a long time. That's what was mined in the 1500s and in the 1600s and 1800s. And it wasn't until the 1950s that there was any significant amount of mining of the sandstone beneath the black shale, which, as you can see in the copper histogram here, there is significant, that's 5% copper. And some of these, there's significant copper in the sandstone unit here beneath the black shale. The black shale is this little unit here. Contains high amounts of nickel, arsenic, cobalt, vanadium, organic material as high as 10% in some cases of organic material, considerable amount of uranium, and of course copper. That's 15% copper in some of the sections of the copper shale, and that's why it was mined in the Middle Ages and supported copper industry from Europe for many, many years. Oh, excuse me, wrong way. So precious metals have been recognized in that black shale, the Kupferschiefer, for a long time. This was Kuku's work in 1982. You can see the little cartoon histograms here of platinum, palladium, and gold up to 100 ppm in this black shale. Sorry. So we're going to look specifically at the published part of in the Kupferschiefer mineralization, the Lubin-Sarowitz district here. And we're going to look specifically at this precious metals horizon, which occurs both in the sandstone and in the lower part of the black shale horizon. You can see on this greatly expanded scale here, this is 0.5 meter in section here. So that's very thin black shale horizon, but it's very rich. And you can see from the work that Borg summarized in 2012 that he thinks that the gold mineralization occurs at the bottom, associated with hematite, and sort of peters out, and the copper deposit occurs slightly above, higher in the section, and with a transition zone between the gold or the precious metals horizon and the copper horizon. So in this district, gold is variable from half a gram per ton to 100 grams per ton. It averages 1.5 gram per ton gold, 0.3 grams palladium, 0.2 grams platinum. It's a thin zone that's not specifically identifiable except by assay, that is 20 to 80 centimeters thick, averages 50 centimeters in thickness, and it occurs over an area of 60 square kilometers. Now that's a huge but very thin gold deposit. It's between 0 and 1.5 meters below the copper zone, largely in the sandstone. And when you calculate some reasonable assumptions about tons and grade, you get something like 2.9 million ounces of gold, 0.6 million ounces of palladium, 0.4 million ounces of platinum. And at current mining prices, it has a value in the ground of something like $8 billion. And it's equivalent to basically a 4 million ounce gold deposit. Now, that's where the gold and platinum palladium occurs, right underneath the black shale, close to this redox boundary of black shale on sandstone, in conjunction with a facies that they call the rotifoila, which is basically it's secondary hematite, oxidation of the sandstones in the lower part of the black shale. Excuse me. There we go. The precious metals horizon in this cross section would lie in between the rotifoila, secondary hematite zone, and the reduced zone of copper sulfides here. And basically, between these two zones within the redox boundary. So the Kupferschiefer copper deposition occurred at between 90 and 120 degrees centigrade. And that's identified and by fluid inclusions and by the occurrence of orthorhombic chalcocite, which apparently is stable only at about 100 degrees centigrade. It was deposited from a highly chlorine-rich sodium calcium chloride brine at a pH of about 6.3, slightly acid, and at an EH of 0.1 to 0.3. So deposited from a warm brine. And the model that Borg proposed in reviewing all of this data in 2012 was this: his T1 facies here is the black shale, and the S1 is the sandstones, the CA is the limestones above the black shale. And he concluded that the metals had been deposited in the front of an advancing redox boundary with copper, lead, and zinc zonation away from the redox boundary. And so we would put the precious metals zone here just in front of the redox boundary. And he saw that this mineralization and alteration was epigenetic. And he and some colleagues of his established in 2010 that it was truly epigenetic. And that is a major reversal in the thought about Kupfer-Schiefer genesis. It has been proposed to be originally syngenetic deposition of copper and other metals directly out of seawater, and that fell out of favor in the 1980s, and then it was assumed to be diagenetic, and very shortly after the deposition of the sediments. But in 2010, Gregor and Simon and several other colleagues established that the copper mineralization actually occurred in two episodes, one at 149 million years that was almost 100 million years after the sedimentation age of the Permian sediments, and then again at about 53 million years. So it ends up that there is now evidence that this is a truly epigenetic deposit imposed upon these rocks long after they had become rock. So are there other sandstone hosted copper deposits with gold? Well, yes, but nobody pays a whole lot of attention to them because generally everybody has assumed, or everybody knows, that copper silver, the copper silver sandstone hosted deposits don't have gold in them. Well, it's not really true when you look at the data. Chambishi in Zambia has 0.3 grams of gold. It's produced 180 million tons of 2.5% copper. The newly discovered deposits in Botswana, some of them at least have 1/4 of a gram of gold. The Lena River deposits in Russia, we don't have a great deal of data on them in Hitzman's table in 2006, but they run between 3 and 6% copper with 0.3 grams per gold per percent of copper. So in the 6% copper stuff, you're talking about almost 2 grams of gold per ton. And Udokan in Siberia, which is a great 1.2 billion ton Proterozoic sandstone hosted copper deposit, has 2% copper and 0.5 gram of gold. And that's a lot of grams of gold in one of these systems. So what other deposits contain precious metals that were deposited from low temperature brines? And those that I found first are the unconformity uranium deposits. the most famous of which are up in the Athabasca Basin, Canada. Some of the others that are less famous but more rich are in the Alligator River area of northern Australia. They also were formed by metal-bearing oxidized brines that interacted with reducing lithology. In this case, when the brines came in contact with a graphitic horizon in the basement, they deposited metals in the sandstones immediately adjacent. There is a polymetallic variety that contains uranium plus arsenic plus nickel, copper, lead, moly, zinc, and platinum. The temperature of the unconformity uranium deposits is generally thought to be between 150 and 200 degrees centigrade. The brine salinities are very high, with 30 to 40% NaCl equivalent in the fluid inclusions from the brines that deposited these metals. Now, in the western part of the Athabasca Basin at Cluff Lake, there's known to be silver, gold, and PGEs in the unconformity deposits there. In the Thelon Basin, which is a similar basin in Canada, there are both platinum and palladium present. At Coronation Hill in the Alligator River part of Australia, there are very high grades of precious metals in small unconformity uranium deposits. Coronation Hill had 5 grams of gold, 2/10 of a gram of platinum, 1/2 gram of palladium. Jabiluka was even, although smaller, much higher grade with 10 grams of gold in these uranium ores. Now, the genetic models that I've borrowed from Cloutier and Byers from the recent James Mollet symposium, they have their unconformity contact type, which is their polymetallic one, where you have a structure in the basement rocks along a graphitic horizon. The brines come migrating through the porous sandstones above the basement unconformity, and it's immediately adjacent to the black shale reductant, or the graphitic horizon reductant, that the uranium deposit occurs. There's a simpler type in many of these basins, particularly the Athabasca, that doesn't seem to, it is largely just uranium, doesn't have the polymetallic signature. So, SEDEX, zinc, lead, and silver deposits also have some precious metals component. And that was drawn to our attention by Paul Emsbo in his paper in 2000, where he described gold in the SEDEX, zinc, lead, silver deposits. And he noted that at Rammelsburg, Germany, which produced 30 million tons of high-grade lead, zinc, silver deposit, it had 1 gram of gold as well. The Anvil deposits up in Canada, similarly, 7/10 of a gram of gold in 120 million tons. And a small occurrence up in Triumph, the Triumph mine in Idaho, had 2.5 grams of gold per ton. Now, these SEDEX, zinc, lead, silver deposits were deposited at a temperature of between 50 and 260 degrees centigrade. The brine salinities are 8 to 28% NaCl equivalent. And Paul concluded that the brines were as well moderately acidic. And Paul has advanced a theory that the brine was generated on a carbonate platform by basically Sabka evaporation up here on the platform, generating a brine that, because of its density, migrated through the sedimentary section and then broke through out to the sedimentary basin, either up faults or through mud volcano type breccia pipe vents into the seafloor. And he's modeled this in some intriguing work that he's done that establishes that as the evaporation occurs on the Sopka platform, the brine migrates and does migrate through the section and then breaks through into the seafloor. So once again, another variety of sediment hosted or sediment replacing deposits that have been, their precious metal content has been largely ignored. Now, this is not exactly my forte in phase diagrams, but it's part of Paul's paper on the gold solubility that he sees in these SEDEX environments. And this section, or this diagram here on the right, is just a blown up version of this one here on the upper left. And we have the stability fields of 200 degrees centigrade of hematite and pyrite, magnetite and pyrrhotite. So iron minerals overlain with, here we have the sulfur species, HS minus, H2S, and sulfate. And so, and these contours here are two contours of the potential concentration of gold in a fluid of this character, excuse me. Okay, so we have 100 ppb gold contour here and a 1 ppm gold in the fluid contour here. And this section here, vertically crossing from the pyrite to the hematite zone, we will see in the next slide, blown up somewhat. And under these conditions of 15% NaCl equivalent salinity, total sulfur is a 1/100th molar, temperature is 200 degrees centigrade. The metals have high solubility in these fluids at relatively low log of oxygen concentration. And gold and barium behave exactly the opposite of what most of the metals are doing. As the log of the oxygen concentration goes up, the gold concentration goes up, and the barium concentration goes up. And Paul said, well, you ought to go look at SEDEX deposits that were low in metals and high in barium, and he thinks that's where the gold ought to be. So as part of this, pursuit of gold in these brines, we ought to take a look at the relationships between gold and chlorine for a while. Now, this has been known for a long time that you could use chlorine to get gold out of resistant rocks. And it was described in the Middle Ages in a description that was even older than the De Re Metallica of Gregorius Agricola in 1540. And it's illustrated here in one of the woodcuts from De Re Metallica, where they are roasting ores with salt. And when you roast ores, gold ores with salt, the oxidizing roast with the salt converts the gold and pyrite and other insoluble gold minerals, converts it to a soluble gold chloride that can then be leached out of the rocks. Now, Emmons did some work on gossans in the early 1900s and investigating the weathering of ore deposits, and he determined that secondary deposits of gold were dependent on chloride solutions, iron sulfides, which maintained acidic conditions and required a strong oxidant, usually manganese oxide. Now, some of that work had already been put to use in the 1800s, where refractory ores were treated with chlorine gas, which formed stable gold chloride compounds, which were then leached from the treated ore. Now, that was abandoned in the 1930s when cyanide turns out to be a much safer way of treating refractory gold ores. And that's been largely abandoned, but the relationship between gold and the solubility of gold in chlorine-rich solutions has been worked on for a long time. Crosskopf added some more data to this, where he added oxygen and iron +3 and copper +2 to the list of potential oxidizing agents. And he confirmed that gold was transported as the ion gold chloride 4 with a single negative charge. And Cloak and Kelly verified that gold was soluble under room temperature experimental conditions in a 1 normal sulfuric acid, 1 molar or 0.1 molar sodium chloride, approximately 6% weight percent of sodium chloride in the presence of manganese oxide. And under those experimental conditions, gold reached 6 ppm in solution very quickly. And the gold could be deposited by an increase in pH, a decrease in EH, or a decrease in salinity. Now we'll take a little divergence into sedimentary basins, where it all begins. And I will advance first a conclusion, and then we'll get to explaining how I got here. So this is the chlorine-bromine ratio in brines, in sedimentary basins. And this is the sodium-chlorine ratio. And we'll explain how this curve gets generated very shortly. But when Paul Emsbo and a number of his colleagues have plotted up the fluid inclusions from SEDX deposits, they fall here. Most of the MVT deposits fall here in this yellow field, overlapped underneath these other fields. This little red field here is the Kupferschiefer. This green field is the unconformity uranium deposits. And down here, right at the tail end of the curve, we have the Michigan copper deposits, in other words, the white pine deposits, and the classic African copper belt deposits. They occur down at the end of this curve, where some very highly concentrated brines occur. So we'll backtrack and figure out how all of this works. But this curve from here, seawater concentration of bromine and chlorine and sodium, this curve represents the evaporation, or the evaporation of seawater, and the sodium chloride and chlorine bromine ratios that change with the degree of evaporation of seawater. Now, this diagram represents the evaporation of seawater from 0% evaporation to 100% evaporation. And the first thing that happens when you evaporate seawater is that you precipitate gypsum. So it takes calcium out of the system, gypsum's calcium sulfate, until the gypsum is precipitated, and then the amount of calcium in the remaining brine drops rapidly. The red curve here is the concentration of sodium, and you can see that the concentration of sodium increases until the salt begins to be precipitated, And then the sodium is taken out of the brine as salt is precipitated. Now there are other curves on here, which are magnesium and potassium, and the chlorine concentration of the brine is fairly stable across once salt halite is precipitated. This chlorine composition of the brine stays relatively stable. These two diagrams represent that the chlorine-bromine ratio and the sodium-chlorine ratio through the evaporation. And those two ratios are plotted against each other in this diagram here. So chlorine-bromine versus sodium chloride. And these ratios are how you identify a brine that was generated by the evaporation of seawater. So the curve actually goes in step fashion from seawater here. This leg represents the precipitation of gypsum. This leg is the precipitation of the halite. And then the final leg of the curve, quote unquote, here is the precipitation of magnesium sulfate and then the potassium salts down at the bitter end of the brine genesis. So now we go back to this diagram that I introduced, and now you have the context that this curve represents the evaporation of seawater. And these are fluid inclusion data plotted in the fields along this curve. And you can see that they all plot to one degree or another, slightly above and to the left of the evaporation curve itself. The divergence of these fluid inclusions data from the pure evaporation curve represents the effects of fluid rock interaction, that the fluid inclusions actually represent the rocks in which the fluids have flowed. And so they don't plot exactly along the evaporation line. But it's hard to argue that all of these deposits were deposited from brines that are evaporated seawater. Now, one of the natural assumptions in sedimentary basins is, oh, well, the brines can be the result of dissolving halite by other water, groundwater or meteoric water flowing through the salt section and dissolving salt and generating a brine that way. And it's not, the data does not support that. On this upper diagram here, the vertical red line separates essentially the field of dissolved, brines that were generated by dissolved salt or by dissolving salt, and brines that were generated by the evaporation of seawater. And you can see in these two here, which is zinc and lead concentrations in some of the Gulf Coast brines, that the metal concentration is increases as the brines get more chlorine rich. So, and besides being interested in the evaporation of seawater in certain sedimentary basins, there are other things that affect how we might go about evaluating sedimentary basins, and they are mostly involved in diagenesis of sediments, which represent the compaction, the catagenesis, or the generation of petroleum and organic acids, and the dehydration of minerals to create overpressure conditions in sedimentary basins. But the generation of residual brines from seawater made acidic by the high content of organic acids and are capable of dissolving and transporting metals. And, besides the base metals, which are commonly assumed in these deposits, both gold and PGEs also occur and are dissolved and transported by these high chlorine acidic brines. Now, when sediments compact, we have this is a shale percent of shale porosity, and you can see when it's at seawater mud interface, it's essentially 50% water, and the concentration of water, or the amount of water-filled pores, drops rapidly. And at 4 kilometers, it's somewhere less than 10% porous. There is some basins have a divergent amount of porosity in the shales here, where at a certain depth, just below 2 kilometers, all of a sudden there are shales that have extra water in the pores. In other words, they're overpressured. There's these pores in these shales are being inflated by extra water. We'll get back to that in a minute. At that same depth in the sedimentary basins, you have the generation of hydrocarbons. Generally, 3 kilometers depth, generally around 100 degrees centigrade. And along with the generation of hydrocarbons out of unmatured organic material, there is a generation of a large amount of organic acids. These are organic acids that are chemically similar to vinegar, which is acetic acid. And on this diagram from Serdam's work at the University of Wyoming, this is increasing temperature, which essentially is increasing depth in a sedimentary section. At low temperatures, you have some organic acids generated. This is the concentration of these carboxylic acids, these acetic acid like organic acids. They're at low temperatures, the acids are eaten up by bacteria. And when the temperature gets around 70 degrees centigrade, that's too hot for the bacteria dies, but the organic material continues maturing and emitting these organic acids. And so the concentration of organic acids may rise as high as 5,000 to 10,000 milligrams per liter. That's roughly ppms. And then this is the zone where hydrocarbons are generated as liquid and then gaseous hydrocarbons. And at higher temperatures, then the high temperatures start breaking down the hydrocarbons and break down the acids at the same time. And so the amount of organic acids drops off once you get beyond about 140 degrees centigrade. So when you look at the brines in sedimentary basins, this is a plot of pH versus total dissolved solids in milligrams per liter from some work by Hanor. And you can see that once you get above 100,000, above 10,000 parts per million milligrams per liter, up into these 10% and higher brines, total dissolved solids in the brines, they become quite acidic. And in the realm of concentration of chlorine and sodium in these brines that precipitate the metals, we're looking at pHs of somewhere around 4 to 5. So not only are these brines chlorine rich, but they're acidic as well. And we'll take one short look at this little aberrant bunch of porosity data in the shales. And what's happening is that at a certain depth, between 2 and 3, around 3 kilometers, illite is recrystallizing, smectite or montmorillonite is recrystallizing to illite. In this one well example, it started at about 7,100 feet, and the crystallization finished at about 10.9. And so we're going from 25% illite layers in the clay to nearly 80% illite layers in the clay. That reaction releases water. And in a couple of these diagrams, and that is the well that we just looked at there. At 7,000 feet, 7,100 feet, it had 9% of bound water in the clays, plus 6% or 5% pore water in the rock. That bound water escapes and becomes is added to the pore water, and that creates extra pores and pressure in the rocks. So this is the origin of overpressure in sedimentary basins. This is another example of a shale going from deposited. This is the amount of water above this line here, the horizontal line in the middle. That's water in the shale. This is solid material in the shale. And you can see through burial, the dehydration reactions release. First, the water escapes through compaction, and then water escapes out of these rocks through dehydration of the clay minerals. Excuse me. So if you're a mud engineer on a oil rig, you're looking at diagrams like this, which represent the depth in kilometers here and pressure in, let's see, thousands of pounds of pressure. And these little diagonal lines here are what the mud engineer actually pays attention to. This is the number of pounds per gallon of mud that he has to mix up to keep that pressure controlled. If he doesn't keep it controlled and keep the mud heavy enough, the well blows out and there's all kinds of recriminations and things that happen. But this line represents a normal pressure zone, a overburden pressure, and an overpressured zone, and then a deeper stable pressure zone. This is a sandy basin where you can see that this pressure builds up rather gradually. And in a shaly basin, it builds up more precipitously to a higher pressure fluid in that rock at that depth. So all of this means that you've got a sedimentary basin that's maturing, and it generates hydrocarbons, it generates acids, it's full of nasty chlorine-rich brines, and under the right conditions, it also generates considerable pressure in the sedimentary basin. That in itself is what helps move the brines around. Now, Paul Insbo advanced this diagram a few weeks ago at the Wale Symposium, and as sort of a evolution of basin-hosted systems. And he was thinking about, lead and zinc and copper and uranium in some of these as well. And only one of them is the unconformity uranium deposits. But we could put we could put the precious metals deposits on this same diagram, where an evaporating basin here creates brines. In rift environments, you get certain types of deposits. In a sag environment, in other words, Paul's Sabka brine model for generating brines produces these kinds of deposits. So the exploration implications of all of this, of sandstone or shale-hosted gold and or PGE deposits with or without significant base metals is captured in this diagram, and that ultimately we're going to be sprinkling precious metals environments on this same diagram. If it is true, and my speculation has some merit, that there will be precious metals deposits that may have these same base metal signatures, may occur with relatively low amounts of base metals, in which they wouldn't be necessarily evaluated for precious metals. But all of these deposits have been assumed by the exploration community to have relatively low amounts, if any, of gold and PGEs. So I'm suggesting that there not only is a largely, shall we say, underexplored varieties of precious metals deposits related to these high chlorine brines and sedimentary basins. I'm also suggesting that we can use a systems approach to exploration for precious metals in sedimentary basins that involves, evaluating and comparing basin styles and histories, comparing the metal source rocks in basins, whether or not the source rocks actually had significant amounts of precious metals dumped in there in the sedimentation events. And then the generation of brines in these basins, and the timing and mechanisms for brine expulsion. One has to remember that these brines are heavier than seawater. Many of them are in the 1.1 gram to 1.2 grams per cc. So they're relatively difficult to move in a sedimentary basin because they're heavy and they don't want to move, and they sink down into the bottom parts of the basin. And then we have to consider brine flow paths. How does this brine get expelled from the basin, and where does it go, and what rocks does it see? And along that brine flow path, what lithologies does that brine interact with that will be metal concentration mechanisms? So this is what I've been working on off and on for many years, of thinking about, all of these things that are going on in sedimentary basins and the relationship between these high chlorine brines and precious metals, and wondering and speculating that there are precious metals types of deposits that have received relatively little attention and probably haven't been explored specifically for their precious metals contents. So from that, that's my speculation. That's the kinds of things that I've been thinking about. And with that, I think I would like to open it up to questions. Of course, Lou has his hand raised.
Yeah, John, I've got a question.
Sure, shoot.
Bruce Geller here. So, which minerals were you thinking yielded the fluid inclusion data in the Cooper Schiefer?
Yes.
Which minerals specifically were being used for fluid inclusion data?
From what I understand, most of it's from calcite veins that occur cutting the copper deposits, and from fluid inclusions in, shall we say, cementing calcites.
Yeah, and along the same lines, what minerals are being used for those two age determinations for the copper stages?
In the Kupferschiefer,
Yeah.
the stagers, that's actually done with a very elegant series of paleomagnetic analyses based on the red beds and the paleomagnetic inclination of secondary hematite that occurs in the redox boundary in those deposits. So it isn't the H determination isn't actually done with fluid inclusions, it's done with paleomagic.
Interesting. Thank you.
Lou had his hand raised.
Hi, John. Can you hear me okay?
Yeah, I can hear you, Lou.
John, thanks for your presentation. Great. Two quick questions. Firstly, have you given any thoughts, or are you familiar with the Belfourche lineament runs through Wyoming, and whether there might be some parallels relates to the Peace River lineament? And then secondly, are you familiar with any hydrothermal, whether it be low temperature or otherwise, remobilization of platinum group metals associated with Bushveld?
Not with the Bushveld. Well, okay. First of all, the questions one at a time. The Belfourche lineament, I'm not familiar with, haven't done anything with it, but okay. Those kinds of basement lineaments are the kinds of places that one has to continually look for their effects on the sedimentary basins that they cut, because they seldom heal. Once they're broken, and they're probably basement signatures, basement structures, they keep being continually rebroken, and they are the places to look for the brine expulsion if you're going to look along a structural zone. But that's a place to look for brine flow paths. And you would recognize brine flow paths by distinctive alteration of the rocks by low temperature but high chlorine fluids. So in terms of the Bushveld, I'm not aware of any low temperature remobilization of platinum group elements there in the Bushveld. That's the realm of the igneous petrologists and high temperature guys, and I quit that stuff many years ago.
Roger that. Thank you very much.
Anyone else?
John, this is Nate Brewer.
Hi, Nate. Yes.
Welcome, fellow UCSB gaucho. Yeah, would you classify the Spar Lake and Troy deposits in Montana in this sort of group?
Yes, they are very clearly Proterozoic age, sandstone hosted, quartzite hosted now, copper silver deposits, and everyone knows there's no precious metals associated with those, quote unquote.
Well, that was my next question.
Well, I worked up there for many years off and on, and I don't remember the people that I was working with ever running gold or platinum in those, on ores or regional samples in those rocks, because everybody knows there's no gold in those systems.
Okay, well, thank you for your presentation. Very good.
So, it's these things that everybody knows, quote unquote, about about the nature of these deposits and the relationships of precious metals and chlorine-rich brines. Well, it needs a lot of reevaluation, and I think that reevaluation presents some considerable, very interesting exploration opportunities, because goodness knows the big gold companies have looked everywhere really hard, except in the clastic-dominated, evaporate-rich sedimentary basins. So that's where I'm looking. Anyone else?
Hi, John. Jim Piper here.
Yes, hi, Jim.
Very good talk. I was wondering, in regards to mining this kind of deposit, where you have, say, a meter of mineralized strata that may be very extensive. How is it mined? I mean, the Cooper-Schiefer, I think years ago, I think somebody said that they were proposing that it be mined through by fluid and not going underground. I know there's been underground work there.
Well, in the Kupferschiefer and in the Lubin-Serowitz district, there are literally hundreds of miles of underground workings that are put in to exploit the copper deposits that are just a meter or so above this gold horizon. So it's all of the infrastructure is already there in this case to exploit something that's only half a meter thick. But if it you look at something that's half a meter thick, if it's in a flat-lying, relatively relatively soft sandstone, you could mine that by underground room and pillar. Yeah, you'd have to take out, say, 3 meters of height, and dilute your half meter. But if some of that runs 100 grams of gold per ton, you can stand a lot of dilution. And those, yes, unfortunately, that deposit in Poland is spread all over the place in a very thin layer. But if the geological circumstances concentrated that much metal in a smaller volume, it could be a barn burner of a deposit. I mean, 4 million gold equivalent ounces of that's a significant deposit. And if you could if you could find it where you could open pit mine it or underground room and pillar it, and it would certainly be worth entertaining. Luke got his hand up again.
Well, I'll ask one more if you're willing. Have you ever given any thoughts to the implication of some of this to the Williston Basin, where there's a considerable evaporite section there as well?
I have not worked the Williston Basin specifically for metals, but it has one of the first ingredients. It has the evaporite section, without which this whole charade doesn't work. So you got to have a source for the salt that's from the evaporation of seawater. That the Williston Basin is basically the southern extension of the prairie evaporite that goes all the way up to Fort McMurray in northern Alberta, where it does have gold and PGEs in it. Well, at least in the brines that we think were sweat out of the prairie evaporite. So it's not unimaginable that the Williston Basin might have precious metals potential. It fulfills the first criteria. It has an evaporated seawater source of a brine. Now you have several other steps to go through to evaluate that basin compared to a bunch of other basins, but it's certainly worth putting on the list for a start.
Roger, thank you.
So what do you know about the petroleum industry in the Williston Basin, Lou?
Well, ever hear the word fracking?
Oh, yes. Yeah, it's a dirty word.
So there's plenty of that ingredient there. Sure.
Yeah. But of course, all of those people that have done all that work in the Williston Basin have done absolutely nothing and gave no thought whatsoever to precious metals in that environment.
Right, right.
John, it's Mary Little.
Hi, Mary.
Hi. Somebody's phone. Anaconda, I had a drilling project on the far eastern end of the Silver Valley in Idaho, in the belt, and there was gold.
That's interesting.
Yeah.
Yes, those deposits, you know, I have not included in my presentation, but the lead silver deposits of the Coeur d'Alene district are not that unlike the, you know, the brine sourced and brine transported metals of these other deposits. They are somewhat more complicated by structural events and structural massaging, I think, but there is some family relationship there still, and that's very interesting.
Yep. Thanks. Great talk.
Thank you. Anyone else? I got time.
Well, if there's nobody else, John, this is Nate again. I just wanted to thank you again for a wonderful talk. It's kind of really opened my eyes to a lot of things that I've seen in my career, and I'm very interested to follow up on some of these ideas. And you know, in normal times, at this point in the proceedings, we would be presenting you with a medal that is the DREGS medal for Distinguished Lecturer, and that medal we'll have to send to you, unfortunately. but at any rate, you know, you've really presented something that I think everybody in the audience has really appreciated here tonight. So.
Yes,
good job.
I can hear people digging through their files, either mentally or physically, thinking about that prospect that they didn't really understand absolutely back somewhere. Yeah, I've got several file cabinets of those kind of memories as well.
I'll bet you do. So, are there any more questions from the audience? All right. I don't, oh, looks like we have Jimmy Roy has his hand up.
Go ahead. Oops. I think Jimmy may be muted.
Yeah.
Yeah, Jimmy, this is Jim Piper. Jimmy Roy is my handle, okay?
All right.
Yeah, another question. The vibrant trend, are there these kinds of deposits in the vibrant trend that you're talking about?
Well, I haven't a great deal of experience, but I would guess that if you go back and look at geochemical files from the mines in the Vibram trend and reconnaissance programs and exploration programs, you'll find reams of analyses of zinc and lead and even some copper in some of those. And I'll bet you find precious little gold or PGE assays. Maybe, you know, 1 in 10,000 rocks has been, you know, that would be my guess of, you know, how much searching for precious metals there might have been in, you know, in the viburnum trend or some of the mid-continent, you know, zinc terrains. So I I think we ought to assay some rocks from there.
Thank you.
Okay, thanks again, John. Thanks everybody for tuning in. And at this point, we'll close the meeting and look forward to seeing you guys all next month, first Monday in November. Take care.
Take care.